So today we're going to be using the heat and mass transfer analogy to derive and explain the Lewis relation, which for Lewis simplifications, the heat transfer coefficient times density times heat capacity times the mass transfer coefficient. And heat transfer, or the heat capacity of air, should probably specify. So first we're going to designate the Schultz number, which we'll designate by SH. And the Schultz number is equal to the length times the mass transfer coefficient divided by the diffusion coefficient, which we'll represent by DAB, as it's A is getting diffused into B. And this is equal to concentration times the Reynolds number to the nth power times the Smith number to the 1/3. So just for clarification, we have the Schultz number is equal to the length times the mass transfer coefficient divided by the diffusion coefficient of A diffusing into B. That's equal to the concentration times Reynolds number to the 3rd times our Smith number to the 1/3. So move this real quick. So we have our Schultz number right here. So now for the next kind of problem we want to focus on is our Nusselt number. And this will be denoted with an NE. And that is equal to our length, our heat transfer coefficient H, times our thermal conductivity K. So again, this can be equal to our very similar to our Schultz number derivation, where we have our concentration times our Reynolds number to the nth power times the Reynolds number to the 1/3. So we have our two numbers that are divided out. So now what we want to do is we want to divide the Schultz number by the Nusselt number. Which is equal to, we can kind of match these up, our length times our mass transfer coefficient divided by our diffusion coefficient of AB, and then on the other side we're just going to flip it, LH over K, so we can cancel out our lengths. So now what we want to do is we want to divide our Smith number divided by our Reynolds number. And we're going to put this to the 1/3 power, which is equal to K over P, our thermal conductivity divided by our density times heat capacity times our diffusion coefficient. And that will be to the 1/3 power. So using this, this can be simplified into thermal conductivity over our thermal conductivity divided by our heat diffusion coefficient, and then times P, our density times heat capacity times our Lewis number. And that's going to be equal to our Lewis number to the 1/3. So if we assume our Lewis number is equal to 1, we can separate these into each other to get KH over PCP-LE is equal to 1. So if we put the H on the other side, we get H equals K PCP-LE. LE is 1. And so we get our equation that we're looking for here, which is our our heat transfer coefficient times our thermal conductivity is equal to our thermal conductivity times our density times our heat capacity. So again, this is through air, so I guess I can make this a little bit more So there's our final equation. Thank you very much. Hello everyone, so today we're going to be deriving and showing the relationship between the wet bulb temperature and the adiabatic saturation temperature. We're going to derive an expression for the molar concentration of water in the air in terms of dry and wet bulb temperatures as well. So to start, we're going to draw our situation where we have our little area. We have a surface. With the water surface, and then we have air flowing over. So we have the temperature at the interface right here, right at this point right here, and we have temperature of infinity, which is very high up, flowing over it. Then we have the temperature of the air that's actually flowing over. So this is the situation that we're going to be dealing with right now. So let's draw our equations. So we have our heat capacity coefficient times our area, and then we have T of the air minus T of the water. And that's going to be equal to entropy of vaporization, which will be used by lambda, our area, our our mass transfer coefficient, and that's times the concentration of the water interface minus the concentration of infinity. So now that we have our equation, we have to recognize what's also going on here. So the air that's flying over is actually supplying entropy to the surface of the water. So with that in mind, we can proceed. So just off of first initializations, you can cancel out those areas where we get H over T air minus TW, which is equal to lambda Kc concentration of water at the interface minus concentration of the water at infinity. So now what we can do next is we can recall our H equals K PCP, or our thermal conductivity times our density times our heat capacity. We can input that for our H value, our heat transfer coefficient. So we have K PCP times our temperature of air minus temperature of water, and that's equal to the entropy of variation or vaporization, Kc, concentration of water at the interface minus concentration of water at infinity. So now we can simplify that down even further. So just initially, our K's will cancel out. So where we get our density times our heat capacity times our temperature of air minus temperature of water. And that's equal to our entropy of vaporization times our concentration of water at the interface minus concentration of water at infinity. So there is our first expression. But now let's work at the adiabatic saturation portion. So at this point, we can visualize our situation that's going through. So let's imagine we have a tube with water running at the edges, and then air going in and out. So temperature 1 is air, and we have temperature 2 over here. And for a reminder, right up here is water. So now we can kind of apply a very similar equation right here. This will have our H value, which is our heat transfer coefficient times our area, and that's temperature of the first minus temperature of the second, and that's equal to entropy of vaporization times our area times our mass transfer coefficient, and then that's times our concentration of water at 2 minus concentration of water at 1. So initially, We can cancel out those areas. We have T1 minus T2, our entropy of variation times Kc. So we can apply the same kind of logic where our heat transfer coefficient is equal to our mass transfer coefficient, or our, excuse me, not mass transfer, our mass transfer coefficient times PCP. So you can input that in. We get the following. So now what we can do is values cancel. So we have P, CP, T1 minus T2, entropy variation. So now what we want to do is we want to isolate that concentration over here. I'm going to move this equation up here. And we're basically going to isolate this. And so we're going to multiply that out. We're going to multiply that concentration out, and then we're going to plus that out on the other side to where we get concentration 2 is equal to concentration 1 plus, or minus, excuse me, plus P, CP, T1 minus T2, all over the entropy of vaporization right there. These are very similar in form to what we did up there, so they can be related to each other from the wet bulb to the adiabatic temperature as well. That's very important for us, our expression for the molar concentration. So thank you very much.